All right, lecture 32 is on Newton's third law. And we're going to spend a little time on this because this can easily be confusing for people. So I'm going to illustrate Newton's third law in terms of a funny story about a horse that I heard when I was a freshman physics student a long, long time ago in a galaxy far, far away. So there's this horse, and the farmer asks him to pull this cart. And the horse says, you know, I know Newton's laws. And Newton's third law says that if I pull on the cart, then the cart is going to pull back on me with an equal and opposite force. So there's no point in me doing that because I'm not going to go anywhere. Who sees his point? It is true that the horse will apply a force on the cart. So I've written that as F sub hc. That's the force by the horse on the cart. Okay?
Okay.
And it's also true that the cart, via this, mechanical device that's attached to his back somehow, will apply a force on him equal and opposite to the force that he applied on the cart. And so I've written that as F sub ch for force of the cart on the horse. Okay? And by Newton's third law, right, that means that F sub hc, that's the force that the horse applies to the cart, is equal and opposite to the force of the cart on the horse. Okay?
Okay.
Do you have your hand raised?
Yeah.
What?
If he's pulling on it, then he's moving this way and the cart's also moving towards the horse.
Maybe that's getting at the right answer. That's right. I mean, it is true that the separation between the horse and the cart doesn't change here, right, in this case. All right? But these pairs of forces, right, the mistake in thinking here is that this is not, so the F sub ch, the force of the cart on the horse, is not acting on the cart, okay? There's only one force acting on the cart, and that is this one here, okay? That's the force from the horse on the cart. That's the only force acting on the cart, okay? What we're going to call them reaction forces, okay? I think it's a good term. I'm not sure if I've heard it before, but maybe I have. So we're going to call force pairs like this the force and its reaction force. And these are Newton's third law pairs, okay? Every time you have a force, there will be a reaction force. It'll be equal and opposite to it, okay?
Okay.
And we're going to spend some time talking about such reaction forces, all right? But let me just point out, though, right? How do we argue with the horse that it actually moves, right? Because Newton's second law says that the sum of the external forces, and we're going to get much more into external versus internal in a later lecture, okay?
Okay.
But these reaction forces are internal forces, okay? They're not external. So the sum of the external forces, right, will determine whether or not there's an acceleration, okay? And so for the purpose of this, we really need to add in another force, and that would be the force of friction, which will always be in the opposite direction that you're moving, right? Friction is that force you feel when you try to slide a block across a rubber surface. It's very hard to do. It's resisting. Whatever direction you go, it's going to pull in the opposite direction. And we'll talk about friction and how to quantify that force also later. But for now, I think we're all familiar with the idea of friction, right? That's why when I throw something across the floor, it comes to a rest, right? Newton's first law says it should just keep on going forever, whatever its velocity is, right?
Yes.
But it doesn't. It stops, right? And the reason it stops is because it's feeling an acceleration, which we call friction. Okay? But for now, let's just write it like this. And so the horse will move as long as the force it applies to the cart, right? So we have to isolate this system. And I'm going to do it by just simply writing a block, and we'll call that the cart. And so on the one hand, we've got the force, we call it H sub C, or sub hc, the force of the horse on the cart. And then on the other hand, we've got a force acting in this direction, which I've written with a lowercase f, which we're calling friction, right? And so this cart will move as long as F sub hc is greater than lowercase f, the frictional force. Okay?
Okay.
If that's true, then this cart will accelerate. Okay? Now, at some point, of course, the horse is and the cart are going to be moving along at a constant velocity, right? So what's going on there? Well, then this F, it actually turns out to be a slightly different F, okay? There are two types of friction, static and moving, or static and dynamic friction. And so you actually experience a lower frictional force usually whenever you're already moving, okay? And so there's some force that you have to apply to overcome that static friction so it starts to move. And then the actual frictional force decreases and you need to apply a lower force to maintain it. And so the horse will be traveling along on the road at a constant velocity, meaning there's no acceleration, which means that the force that he's applying is equal and opposite to the frictional force he's experiencing as he travels along. And we'll do plenty of problems like that in the homework, and we'll probably talk about problems like that more in the future. But for now, I just want to point this out. Okay, the reaction force, right, or the force pairs, the Newton's third law forces, right, aren't acting on the same body, and therefore, right, they're not going to cancel each other out in the sense that the horse was thinking. Okay.
Okay.
The only thing that's going to make it impossible for him to move forward is if this frictional force is so large that he doesn't have the ability to pull with a large enough force to overcome it. Okay.
Okay.
If that was the case, he'd have a point. So if this was instead of wheels, we had a flat bottom and was dragging on a rubber surface, then he would have a point. Maybe I shouldn't even bother because I'm not going to go anywhere.
All right.
Okay. Reiterate one more time that this being equal to the F sub hc being equal to minus F sub ch is not because of Newton's second laws. It's not because the sum of the forces equal, and the acceleration is 0, right? And then you would solve that. That's not why this is the case. This is the case because of Newton's third law. Okay, let's now talk about contact forces. Be done with my horse here. And there's going to be two contact forces I'm going to talk about, okay?
Okay.
And that is a normal force and tension, okay? You've probably heard of tension before. If I take a piece of rope and I pull it taut, there's tension in the rope, and so we're going to talk about that. Normal force you probably haven't heard before, but you've certainly experienced it a lot, okay? So I'm going to write, first, the things that are relevant to Newton's second law, right? Here are the forces that you would use in Newton's second law for a block at rest on a table, okay? So here's the table, here's the block, okay? So the first thing we have to do is we have to imagine, right? Well, actually, we don't need to do that, but we can just simply say that there is a force of gravity, F. I'm just going to call it F sub g for force of gravity, pulling downward on the block, yes?
Yes.
There is a normal force acting on the block from the table. The table is pushing up on the block, okay?
Okay.
And both of these forces, you notice, are acting on the block. This is the table pushing on the block and Earth pulling on the block, right?
All right.
Both forces are acting on the block. Therefore, Newton's second law is applicable here, right? And so we would say that the sum of the external forces is equal to the mass times the acceleration. Mass, and this is a block of mass m, times the acceleration, okay? But we know it's not accelerating, okay? There's no acceleration, it's equal to 0, okay?
Okay.
Now we can write in the sum of the external forces. What are they? Well, we've got F sub g plus n, and that's equal to 0, okay?
Okay.
Now, some people falsely think that the normal force is the reaction force for the weight, right? The force from gravity, okay? That's not true, okay? So these are, I'll call these the N2 forces. Now I want to look at the reaction forces. Maybe I'll just call them reaction forces. Reaction forces. Okay? So I'm going to draw the block again, okay? And the table. And this time I'm going to put the Earth in, okay? I'm going to make it curved so we know that that's the Earth, all right?
All right.
So there's a normal force acting on the block, which means there's an equal and opposite force acting on the table, okay? And I'm going to call that N prime, okay?
All right.
There is the force of gravity acting on the block, which means that the block is acting on the Earth as well. And so it's equal and opposite. So there is we'll call it F sub g prime. Okay, that's the block acting on the Earth, right? So the Earth is feeling that force from the block, okay? And it is equal and opposite to the force that the block felt due to the Earth, okay? These forces you do not include in your use of Newton's second law to calculate how things are moving or changing or not moving and changing, okay?
Okay.
These reaction forces are not to be included. They are internal forces, and Newton's second law is concerned with external forces, okay?
All right.
Because, again, right, N prime is not acting on the block, it's acting on the table. And F sub g prime is not acting on the block, it's acting on the Earth, okay?
Okay.
So when we do problems in the future, we're going to have a couple of lectures on statics and dynamics. Statics are where everything is not moving. Okay, these are things like houses, right? Houses hopefully don't move. If they did, they'd fall on you, right? But there are forces inside there, right? Things that are holding things up. Okay, and so we'll consider those external forces, and how these kind of statics problems work. And then dynamics, that's when things are accelerating, okay?
All right.
And we'll talk about some examples there, like pulleys and things of that nature. But yeah, so these internal forces you do not use when you work with Newton's second law. And also, the normal force is not the reaction force to the weight of the block, okay?
Okay.
A lot of people think it is, and that's just dead wrong, okay? There is a reaction force to the normal force that is equal and opposite to it, that is acting on the table, but it is not the weight, okay? Now the magnitudes just turn out to be equal because these are not accelerated, because if you look at this, you know, well, this says that if F sub g plus the normal force is equal to 0, then F sub g is equal to minus the normal force, okay?
Okay.
And we can say, okay, well, how do we figure out what F sub g is? Well, we could imagine removing the table, right, in which case this block of mass m is going to accelerate with acceleration minus g, right?
Yeah.
And so we can say, well, the magnitude of F sub g, using Newton's second law applied to this problem without the table present, right, would give us that it's equal to the mass times g, right?
Yes.
And then we can say that's equal to the minus of the normal force, okay?
Okay.
So we can solve for the normal force and see that that's the magnitude of it. But they are not the same force. This F sub g, right, there is a force law that we're going to get to very soon called the law of gravitation. This is Newton's contribution as well, where we have another way to write this force, okay? It is not true that even with the table absent that the force is equal to, this is not the force, okay?
Okay.
This is the change in the system that we're looking at, okay? If this is the only force we have, then we can get the magnitude. It says the magnitude of this force is equal to the mass times the acceleration. But the mass times, that's not the force. There's actually a force law we can put in explicitly to define what that force is. And it has to do with how far away the Earth is from the object that we're considering, okay?
Okay.
And it's a little more complicated, so I'm not going to really go into any detail. Same thing with the normal force. What is the normal force? Well, it's electrostatic, right? And so it has to do with the electrons in our shoes and the repulsion they feel as they get too close to the electrons in the floor, okay? And though I don't think we'll ever be able to write, a single equation that captures what that electrostatic force is in general, it's just too complicated. The magnitude of it, however, we can get because we know that it must have the same magnitude as this force of gravity, right? So we'll just say the normal force is equal to the mass of the object times the acceleration due to gravity. Okay, so normal force on Earth would be, m times g on Earth. The normal force on Mars, if you're standing on Mars, would be m times the acceleration that you would feel on Mars. Okay, it'd be a slightly lower number, but not that much. But that's not actually the force itself. We can write a force law to it, right? And so this would be some combination of Coulomb's law, maybe even quantum mechanical, and it's not something that we do. But that force, the normal force, is a horribly complicated force that I suppose you may be able to write down. You can certainly simulate it. But we will find other ways to replace it with a number that represents the magnitude of that force. But it is not the force itself, okay?
Okay.
And so we'll see that. So let's move on to the other contact force, the tension. And then we'll do a simple problem. Tension. This one is tough to draw, boy. I tell you. So here is my mass, my block of mass m, and I'm going to put a string on it. I'm making the string look a little bit like a spring, just so I don't write it as a line, since we're using a lot of lines here, right? There we go. That's a hand. Does it look like a hand? It looks somewhat like it. Maybe I could give another finger mark like that. Okay, so this hand, right, will be applying a force on the string that's in this direction. Okay? Counter to that will be a force which we'll call T for tension. And it will be the string acting on the hand. So this force that I apply to the string, right, is some force I'm applying to the string, and the string has got its reaction force through Newton's third law of the tension on my hand. Okay?
Okay.
As we move down, though, right, this tension is applying itself everywhere to the string, right?
Yes.
So you can think of like the first little bit of the string, right, is going to be getting a force in that direction, and there will be a tension pushing back on it in the opposite direction. I drew the arrow the wrong way here. Sorry. There. The tension is the equal and opposite to this force here. And so on the other end, we're going to have this other tension, which we'll call T prime, and that will be acting on the block. So I'm actually connected to the block here. Okay? That is the string pulling on the block. Okay?
All right.
Actually, I'll change the primes. I'll put this one here and this one here. So T is the force applied to the block. So we'll have the normal force. And then, of course, we'll call it just W for the weight. That's the force of gravity, which we call weight, right?
All right.
So isolate the system. That's the first thing we want to do. Okay? So ignore the hand. Ignore the string. Okay? Because the string, this tension that I'm talking about here, if we like imagine like a little portion of the string and just isolate that, we'll have a force pulling in this direction, F, and we'll have this tension, or tension prime I called it, pulling back in this direction here. Okay? That's if the mass of the string is very, very small. So if I look at this, I'd say that F plus T prime will equal mass of the string, that's this little section of string here, times the acceleration, right? Well, if I let the mass of the string be really small, right, much less than 1, this is the way we write really small. We say use 2 inequality signs, okay? And that reads the mass of the string is much, much less than 1, okay?
Okay.
So you can say it's approximately 0. And if that's the case, then that means that F is equal to minus T prime, okay? Because the acceleration times whatever it is times 0 will be 0, okay?
All right.
So I've kind of put a 0 in here. That means that this force will be equal to the inverse, the equal and opposite to that tension, okay?
All right.
So that's one point. What about in the, so if I call this the x direction, I call this the y direction, right? Now I need to put some coordinates in here, right? Now that I put some coordinates in here, I can imagine a ruler going along here and a ruler going up and down here, right? Now I can break this down into its components, right? This is, in general, we haven't talked a lot about it. This is called superposition, right? When we're able to break these things down into their components, right? And these different components don't influence the other components, okay?
Okay.
So I can break it down into forces in the x direction and forces in the y direction, or the up and down. So in the y direction, right, I know that the sum of the forces in the y direction will be equal to 0 because there's no acceleration in the y direction, yes?
Yes.
So what are the sum of the forces? Well, that's just the weight plus the normal force, okay?
All right.
And we might need this if we had if I was going to put friction in here, but I'm leaving friction out. I'm saying the friction is 0. But when we talk about friction, we'll need this result in order to evaluate what the frictional component is, okay?
All right.
So no change in the x and in the y direction. But in the x direction, what does that look like? So the sum of the forces in the x direction, well, there's only one, right? It's t, okay? And that will be equal to the mass times the acceleration in the x direction, a sub x, okay?
Okay.
But as we look at over here, right, we know that through Newton's third law, right, that T is equal to minus T prime, yes?
Yes.
That's just its reaction force, right? And from this evaluation of the string, and this, when I looked at this problem here, this isolated system, right, I found that T prime was equal to minus F, right?
Yes.
And so that means that T is equal to minus F, which is equal to F. And so I see that this force F that the hand originally applied to the end of the string, right, has been passed on to the block, right, by a tension. And so it's equal to mass times the acceleration due to x. And so now we can say, well, what's the acceleration? The acceleration is equal to F over m. Okay?
All right.
And if I say that F is equal to, say, 1 Newton, and the mass m is equal to, say, 1 kilogram, right? Then the acceleration that I experience, that this block experiences, is going to be 1 Newton divided by 1 kilogram, which is going to be equal to 1 meter per second squared. Okay? The proper units to use are kilograms for mass and meters per second squared for acceleration, meters per second for velocity, and newtons for force. Okay? If you use those, then you'll get the answers in the units that you want. In this case, meters per second squared. Okay?
Okay.
So, I know this doesn't, you're like, well, God, this was not a very impressive example to work out, right? It seemed like a lot of wordiness. Well, the key, though, is that the physics behind it, right? The way that the hand, right, we analyzed this, isolated this part of the system, where the hand is pulling on the string, right? We assumed that the mass of the string was negligible, and that we could write that these two forces are equal and opposite, right?
Yes.
And so we kind of were transferring the force down the string, right? And that's how you're getting a force on the block. Okay, it's not direct. Okay?
All right.
Now, when we talk about gravity, right, we're going to come up with this problem of action at a distance, and it's really strange because there's no string, right? Whenever something is being pulled by a gravitational force, there's no string attached to it. So how is it getting pulled? And we kind of think about it just like I talked about this. Okay, we think of it as a string, but we call it a field. Okay,
Okay.
and at every point along the way, the field, right, has a change in momentum that's kind of being propagated along. Now we're not going to go into the details of that because that's rather complicated. But the analogy is there: is that by introducing this new thing, the field, we can kind of understand how action at a distance works. Okay.
Okay.
Okay, I think that is all that I wanted to say about this stuff. Yes. So we went over Newton's third law and some of the common misconceptions with it, right?
All right.
In particular, the internal versus external forces, right? The internal forces of these force and reaction force pairs, right? That's Newton's third law, okay?
All right.
And then we distinguish that from the external forces that give rise to motion of a system, okay? That we
Okay.
use Newton's second law for, okay? Cleared up some misconceptions there, like the normal force is the reaction force to the weight. It's not true. There is a reaction force to the normal force that's equal and opposite to it, but it is not the weight. The weight is a force acting on the block, and it has a reaction force which acts on the Earth, okay?
Okay.
But when we solve Newton's law problems, which we'll do more of, right? And I don't want you to think that I've given you all that I'm going to give you on how to solve Newton's second law problems, because we'll talk about statics and dynamics in some detail.
All right.
But we did kind of discuss that, right? How to do these kind of Newton's second law problems. And then we talked about contact forces, right? The normal force in particular, and also tension, right? Which is this force in a string, right?
Which is very important.
Very important, yes. And we kind of mentioned friction, but we haven't really talked about friction yet. But we'll talk about friction because it makes the problems a little more interesting to work with. Okay?
Okay.
Any questions?
I want you to remind me of the misconceptions.
About the normal force?
All of them.
All of the misconceptions? But the one that I spoke about here, right, is that the horse thought that because there's an equal and opposite force on the cart, right,
He thought he wasn't going to be able
he
to.
thought he wouldn't be able to move. But those forces are not on the same body, right? Newton's second law, when you try to determine changes in motion, right, you have to isolate the system, isolate one body, okay, and look at all the forces external to it acting on that one body. And so for the cart, there's only one, and that's the force of the horse. And then if we throw friction in, right, then there's friction. And so all the horse has to do to move the cart is overcome friction. If there was no friction, then any force the horse would apply would accelerate the cart, okay?
Yeah.
Okay.
Yeah, so that's kind of the chief misconception, I suppose. All right, that's it for this lecture.